Okay. So the question was that with what velocity we should project this charge so that it just touches the upper panel, right? This was the question, right, Aisha?
Yes, sir.
Yeah, so let me draw the diagram here. Okay. So, but firstly, thank you for the homework, right? So you just tried those problems and you're regularly trying those problems. So that will help a lot. Are you finding that it is helping, Aisha?
Yes, sir.
Yeah. So we projected some charge with some initial velocity, right? With some 45-degree angle. And it would have a x component, right? That would be u cos 45 and the y component u sine 45. So this is uy. Okay. So in the equation, you have to use uy or u, right?
Mm,
Ui. So you have found out the value of ui. Okay. And you have found out the value of ui. So you can calculate ui is how much. So only two steps were missing. Ui is u sine 45 degree, right? So Uy, this is 2 into 10 to the power 6 meter per second. And this U you need to calculate and sine 45 is how much? So this would be 2 root 2 into 10 to the power 6 meter per second. Okay. Understood, Aisha?
yes, sir.
And Mariam and Saad, you guys didn't try the problem, so you don't know what is happening, right? You guys, am I correct?
Yes, sir.
Yeah, so you guys should try those problems, right? Okay, so let us start where we stopped. So we were doing this electric flux, and up until now I talk about. So let me revise again a small recap. So we studied that what is electric flux. So what is the electric flux? Saad, do you remember? So if we have a surface, let's say this kind of surface, right? And electric field lines are passing through this surface. Okay. So this surface will have a direction. This surface will have a direction. And for this case, the direction is normal. So this is normal and this is electric field, right? So you can see that this normal is with making 0 degree with this electric field. So the electric flux is defined as the number of electric field lines passing normally to the area, right? So this is the electric flux that we discussed, and we then talked about. So this is represented by phi, which is E dot A. Okay, and cos theta when it is making some angle with the normal. So let's say that we have a sheet. Okay, this planar surface, and it has a normal vector this. But the electric field line or electric field is in this direction. Okay. So this is making an angle theta with this normal. Okay, guys. So then this cos theta. Right, we discussed this in the previous class. Right, we discussed this. Okay, guys.
Yes, sir.
Yeah, so the surface that we talked about was the planar surface, right? Planar surface meaning that these kind of surface. Okay, this kind of surface. And what kind of surface? Let's say square surface. Okay, so this is a rectangular surface, right? Rectangular surface. And this is a circle, not a sphere. So this is a circular surface. And this is a square surface. So for these kind of surface, what would be the area vector? This would be normal to this, right? Again, normal to this surface. So this is the direction of the area vector, right, guys?
Yes, sir.
So for these kind of surface, we calculated the electric flux, which was simply what? Which was simply EA, E dot A, right? So this was the electric flux. And as Aisha asked earlier, that it was a scalar quantity, right? It is a scalar quantity. And secondly, that its unit is how much? So this electric field is Newton per coulomb, and this is meter square. So SI unit is Newton per coulomb meter square. And we can also write it as voltmeter. Okay. So these are the SI unit of electric flux. So this due to this plane surface. Okay. But what happens when you have a curved surface? So can you guys give an example of a curved surface? Yeah.
A
Can you
cone.
a cone? Yeah. So a cone has two parts. A cone has two parts. This is, let's say, this one and this surface. So the bottom surface is circular, right? And there is a slant surface. So the slant surface is curved, right? Slant surface is curved, but the bottom surface is circular. Yeah, so the curved surface area of the cone. Okay, and another example, Saad and Mariam, can you guys think of another example of a curved surface?
Cylinder. Cylinder.
Yes, of course. Yeah, very good, very good. So for the case of, yeah, I have the shape of cylinder, right? So this cylinder has what kind of surface? This one surface, right? And this surface and this surface. So these two surfaces are of the circular type, but this surface is the curved surface, right? So this is the curved surface of a cylinder, and these are the circular ends. Okay, guys. So the example of a curved surface would be, so for surface, curved surface. First, the example of curved surface are what? Cylinder, as Mariam said, and as Aisha said, cone. So, and you guys have seen the other example regularly. So you see what? You see apples, you see not the perfect apples, but you see what? Footballs and something like that, right? So those are spheres, right, guys?
Yes,
So spheres are also the example of curved surface, right? So what happens in the case of this curved surface? So let's say you have a curved surface, okay, and what would be the direction of the normal vector? So the direction of the normal vector at this point would be this, right? At this point, this would be this. At this point, this would be this, and at this point, this would be this. Okay. So let's say that you have an electric field which is this, So these electric field are uniform, but you can see that these angles, this is theta, let's say this is theta 1, this is theta 2, this is theta 3, and this is, so this is theta 4. So what is changing? Oh, left. Yeah, you guys are there. So you guys can see the difference. So for the plane surface, let's say this is the electric field, right? And let's say this is the electric field. So for the plane surface, this angle was always what? So this angle was always, yes, guys, can you tell me this angle was same or different? Yes, Aisha.
What did you repeat?
Yeah, so for the case of plane surface, the angle that the normal makes with the uniform electric field is always what? Same or different?
Same.
Yes,
Same.
same, right? Because you can see that these angle are same, right? Let's say you have this, let me draw it here. So let's say you have this surface, right? And the normal vector is this. And this is the, so you guys can see that this angle is always the same, right? So this is theta, this is theta, this is theta. For the case of this plane surface. But for the case of this curved surface, what happens is that this theta changes at each point, right? So this theta changes at each point. So calculating the flux would be difficult, right, guys?
Yes, sir.
Yeah, so what we do is that we take small patches, infinitesimal small patches of this area element, ds. And this area is in the direction of this. So this theta remains the same for this small element, this small area element. Okay, understood?
So could you explain again?
Yeah, so let's say you have this small element ds, okay, and this is the electric field, and this is, let's say, normal. Let's say this is, okay, so let's say, let me draw that this is the electric field, right? And this is the normal. So the small element is small angle element would be d theta. Okay.
Yes, sir.
So for this case, this area element or this flux would be E dot ds. Small flux would be E dot ds. Understood?
Yes, sir.
And if we want to calculate the whole flux, so then we will integrate in the entire range. Understood? So we'll integrate from here to here. Understood? So flux would be integral of E dot ds, right? And this would be a surface integral. Okay. Understood?
Yes,
Yes.
sir.
Yeah, and what we do is that we make this angle same. So for this area, this would be in the direction of this. So this area would be, so the normal to this area would be same, right? This would be the normal and this would be the electric field. So that is how we make this small area element ts. Okay, so this becomes this cos theta, this theta becomes 0 for this small element. And this becomes E ds simply.
Sir,
Understood? Yes.
sir, why is theta 0?
Yeah, because let's say that you have this, let's say you have this electric field, right? And I have taken this area element in the direction of this electric field. Understood? So the normal to this vector would be in the same direction as this electric field. Okay, I have taken my small area element like this. Okay, if I take the area element like this, so this would be in this direction. But I have, by choice, I have taken the area element. I have taken the area element in this direction, small area element. Understood? So small
Yes.
area element in this direction, and small area element in also in this direction, small area element in this direction. And then what I do is that I integrate all these small area elements. Understood? Yes.
Yes, sir.
Okay. So then this would be the electric flux for the curved surface. And this S shows the surface integral. Right. Understood?
Yes, sir.
And what happens if I have the surface? So I have another integral which is defined like this. So for this case, you can see that there is a circle over here, or this is closed loop. So this represents a closed loop, which means that my surface is closed. Understood? So this represents my surface is closed. This represents my surface is open. So let's say that I take a cylinder, right? I neglect the, so let's say that in the both side the cylinder is open. So this is an open cylinder, right? In both sides the cylinder is open. And I take, so for this cylinder, right? For this cylinder, what I do is that this is the electric field. Okay. And I have taken this small area element. So this would be in the direction of this electric field. Understood? So this is an open surface or a closed surface?
Close surface.
Close or open? So this is a close or open surface. You guys see and tell me. Close or open surface. This part is not there. This part is open. So close or open surface?
Open.
Open.
Open surface, right? So this, the area for this cylinder would be, this ds would be, let's say that E, my electric field is constant, right? So this ds would be how much? This ds would be simply 2 pi RL. This is the curved surface area of the cylinder, right? Understood, guys? Any doubt in this problem?
Now, what is the other integral called?
What is the other?
Integral called?
What is the other integral called?
Like in the surface closed?
Yeah, so this is closed surface and this is open surface. So if I integrate like this, let's say like this, so this is open surface integral. And if I write the integral like this, so this is closed surface. So can you guys give me an example of a closed surface integral? Yes. One example of a closed surface integral. Yes, guys. You may have seen it in many a times. You have seen that that kind of shit. So sphere, right, guys? Sphere is a closed surface, right?
Yes, sir.
So example of sphere is a closed surface. Okay. Understood, guys?
Yes, sir.
Yeah. So for the case of the for the case of this for the case of this sphere, right? And this is ds. So if I integrate this ds in this closed surface, so this would give me how much? The area of the sphere. What would be that? Let's say this is R. Yes, guys, tell me. This would be what?
By R.
Yes, absolutely right. So 4 pi R square. So understood the difference between the open surface and the closed surface? Yes. Did you guys understood the difference between the closed surface and the open surface? Understood?
Yes, sir.
Yeah. Saw any doubt in the open surface and the closed surface analogy? Yes. So you guys please note this down. Note down this part, and then I will talk about this Gauss law, right? So just remember that for cylinder, for the open cylinder, this would be the open surface, and for the sphere, it would be a closed surface. Okay. Yeah, so if you guys need me to scroll down the screen, then you guys tell, then I will scroll down. So up to this point, we learned about that for the plane surface. For the plane surface, for the plane surface, this flux would be simply EA cos theta, E dot A, right, guys? But for the curved surface, we have to take the small area element and then integrate the area element in the entire range. Understood, guys? Any doubt in that part?
No, sir.
Yeah. And why did we do that, Mariam? Why did we do that? Why did we take the small area element? Yes, Mariam, why did we take the small area element? Yes, Saad, can you tell me why did we take the small area element? Yes. Okay, Aisha, you tell me why did we take the small area element?
Because the angles small.
Yeah, because the angles were changing and we can't calculate the flux in the entire surface. Okay. So we need to take the small area element so that the area direction and the electric field direction becomes the same. And then we can integrate the whole integral. Okay. Yeah. So this
Yes.
was yeah. Did you guys note down this part?
Yes.
Yeah. So I should put the screen here. Or did you guys note down the whole part?
No.
1 second, sir.
Okay. Okay. Yes, done guys.
Yes, sir.
Saad and Mariam. Saad, done.
Yes, sir.
Okay, so let us do one question, right? And then we will talk about this cost. So let's say that I have put a Q charge at the center of this sphere. Okay, my sphere is very bad. So let me use this. So, okay. Yeah, and I have put a Q charge at the center. So you guys can tell me that the electric field lines would be this. Right, guys? So I am calculating the flux through this surface. Okay. So I take the small area element, right, ds, and you guys can see that this is in the direction of the electric field. Right.
Yes.
And this sphere is a closed surface or the open surface? What kind of surface?
Closed surface.
Yes, absolutely right. So my phi would be integral of this E, and you see that the area vector direction and the electric field is in the same direction, right? It is going radially outward, right? Radially outward. So this would be only E ds. Right, guys? Understood?
Yes, sir.
And this is r distance, right? So what would be the electric field at this point? Yeah, electric field at this
KQ
point would, yes, kq
by R
r square,
square.
right? And this is ds. Okay, so this is constant. This r is constant. I should write the capital ones because yeah, so I should write the capital ones. Okay, guys. So these are constants, so I can take it out of the integral. Understood? And this is ds. Yes, so you guys tell me what would be the value of this? Saad, you tell me what would be the value of this? Yes, Saad, what would be the value of this integral? Remember, this is a sphere.
4 pi r square.
Yes, absolutely correct. So this is r square, this is 4 pi r square. So k is 1 by 4 pi epsilon naught r square, and this is 4 pi, this is q r square. So r square cancels, 4 pi cancels, and we have q by epsilon naught. So you guys can see that what is the value of flux inside a closed loop? This is q by, and this, let's say, I can write it that as this q enclosed in the surface. So this is q enclosed by epsilon. Okay. So for a closed surface, my flux phi would be how much? Yes. For a closed surface, my flux would be how much?
Q by epsilon.
Yeah, q enclosed by epsilon. So you guys note down this part, and then I will talk about this Gauss law. Okay. Any doubt in this question? Guys, any doubt?
No, sir.
Okay. So now we are reaching the end. We can complete this chapter in next class. Yeah, whenever you guys have noted down, please tell me, then I will talk about it. So I will talk about the next topic.
Done, sir.
Done. Mariam and Saad, done.
Yes, sir.
Yeah, so you
Yes,
see
sir.
that flux for a closed surface is q by epsilon naught. So this is what is called the Gauss law, right? So what is a Gauss law? It says that total flux through a closed surface is 1 by epsilon naught times the charge enclosed. Okay, so this is the Gauss law. Understood?
Yes, sir. Uh, yes, guys, am I audible?
Yes, sir.
Sorry for the interruption. I got disconnected. So light went off and I got disconnected. Yeah, so where was I? Let me share my screen first. So I was talking about this Gauss law, right? So for a closed surface, the flux through this closed surface is 1 by E naught epsilon naught times the charge enclosed, right? So what are the properties of this Gauss law? So let us understand about these properties of the Gauss law. right? It says that the flux does not depend upon the shape and size of the surface. Okay, so what do I mean by that? I mean that let's say I have this surface, right, and this is a charge q, and let's say I have this surface, this is filled, right, this is closed, and I have charge q here. I have this kind of surface and I have charge q. Okay, and let's say I have what kind of surface? Let's say I have this distance, which is so this is, let's say, r, and I have, let's say, this distance which is 2r, and this is q. So you can see that this size is different, but for all the cases flux would be epsilon q enclosed by epsilon naught. For this case also q enclosed by epsilon naught. For this case q enclosed by epsilon naught, and for this case also q enclosed by epsilon. Right, so you can see that this flux does not depend upon the shape and size of these figures or the surface. Understood? Yes, guys, understood.
Could you explain again?
Yeah. So this flux through the surface, according to Gauss law, does not depend upon the shape. So this is a spherical shape, right? This is a cylindrical shape, and this is a random shape. Okay. So for all these shapes, the flux would simply be q by epsilon naught, q enclosed by epsilon naught. So this is only dependent upon how much charge is enclosed. Understood?
Yes, sir.
And this figure tells that it does not depend upon the size of the sphere. So here the size was small, here the size was bigger. But for both these cases, the flux was same. So this tells that this flux does not depend upon the shape and size of the surface. Understood?
Yes, sir.
Yeah. And the second property is that so it does not depend on outside charge. Okay, let's say that I have let's say I have these three charges, let's say Q1, let's say minus Q2, and let's say Q3. Okay, and I have other charge which is Q4. So flux in this on this surface would be simply Q1 minus Q2 plus Q3 by epsilon naught. It will not depend upon this outside charge. Okay,
Yes.
understood? Yeah. And the third property is that so for the case of outgoing electric field lines, flux would be positive. Okay, and vice versa. What do I mean by that? So let's say I have a closed surface, right? And the electric field lines are like this. Okay, so for this case, flux would be simply Q by epsilon. Understood? And let's say I have these kind of electric field lines. So my flux would be how much? Naisha, my flux would be how much? Yes. Yes, Asha, can you listen? Can you? Yeah,
Minus Q.
minus Q. Yes, minus Q by epsilon. So my flux would be negative. Understood, guys?
Yes.
And the fourth property is that if you have same number of outgoing and incoming electric field lines, right, then flux will be 0. Right. Let's say I have a spherical surface, and so you can see that how many lines are entering. Right. So how many lines are entering, Mariam?
5.
5, right. And how many are outgoing?
5.
So for the case of entering lines, what would be my flux? So how many lines are entering? 1, 2, 3, 4, 5. So minus 5, right? Because for incoming, this would be minus. And for these lines, what would be the flux charge?
Um,
So flux is number of electric field lines passing through the surface. So how many lines are passing?
5.
5. And these are outgoing. These are outgoing, which means that this would be positive, right? So this
Yeah.
would be plus 5 or minus 5?
Plus 5.
Plus 5. So minus 5 plus 5 would be 0. So if you have same numbers of incoming and outgoing lines, so the flux would be 0. Understood?
Yes, sir.
And let us understand about this last property, that flux due to a dipole would be 0. Right? Why this would be 0? Let's say that you have, let's say that you have a surface, right? And the dipole is this. So this is plus Q, then this is minus Q. Okay. So the flux would be Q by epsilon naught minus Q by epsilon naught. Total charge is how much? Q minus Q. Right? Q enclosed is Q minus Q. So this would be 0. Understood, guys?
Yes, sir.
Okay, so you guys please write these, and then we will do some questions, right? So yeah, you guys have already written this Gauss law, right? So whenever you need me to, any doubt up to this point, guys, any doubt?
No, sir.
Okay. And sorry, Aisha, the NEET class won't happen today because I have to go somewhere. So sorry about that. What I will do is that I will take some extra classes at some point later. Okay, Aisha.
Yes, sir. No problem.
Yeah, sorry about that. Sorry about, I didn't want to, but I have some work to do. Okay.
Okay, sir. No problem.
Hey, you guys, please note it down, and then we'll discuss further. So we'll do some problems, then you guys will understand. Yeah, so you will be able to understand it more. Yeah, so whenever you guys need me to scroll down the screen, you guys please tell me. Okay,
Done, sir.
done. Saad and Mariam, done.
Yes. Yes, sir.
Done. Who said done so quickly?
Me, sir.
Your voice is breaking, Mariam. I don't know. Maybe your internet is not stable or mine is not stable. Oh, who left? Yeah, so Saad got disconnected. Yes, Saad got disconnected. Oh,
Yes, sir.
oh. So did you note down this part, the third part?
No, sir.
Okay, yeah. Please. Any doubt, Saad, up
No,
to
sir.
this? Oh, good, good. Yes, done, guys.
No.
Done. Saad and Mariam, done.
Yes, sir.
Yes, sir.
Okay, so just quickly note these two properties and then, oh, 4 and 4. My counting is bad. This is for the in a closed surface, right? So we are talking about this closed surface only. So all these examples are for the closed surface. Yeah, whenever you guys have finished, please tell me.
Done, sir.
Done, sir.
Hello, yes, guys, can you hear me?
Yeah.
Yeah, sorry for the interruption because so light went off and then I got disconnected and so I'm trying to connect again and again and it is not connecting. So you guys, thank you guys for your patience because so thank you guys. So you guys are waiting for 15 minutes or so, right?
Yeah.
Yeah, sorry about that. The light went off and Wi-Fi or other thing got disconnected. So I'm working on it now and yeah. So we understood one point, right? We understood one point that when we calculate the flux inside or the surface where that surface is closed, right? So if we calculate the flux for a closed surface, so that would be simply how much? Saad. Yes, Saad, are you there? Or you are not? Saad, can you hear me? Okay, so maybe Saad is roaming around here. And there. Yeah, so Mariam, can you hear me?
Yes, sir.
Yeah, so let's say that if you have a closed surface, any kind of a surface, let's say it is a cubical closed surface. And I tell you that I want to calculate the flux through that surface, through that cubical surface. So what would be the flux?
Q by epsilon 0.
Q by epsilon naught, right? Q by epsilon naught, any kind of surface which is closed. So let's say that I want to calculate the flux inside flux through a closed surface, which is a cylindrical surface. So Aisha, what would be the flux then?
That would be
Yeah, that would be Q by epsilon naught, right?
yes.
Yeah. So the next set of question would be based on that. We have to understand that if we close the surface, then the flux would simply be how much? Q by epsilon naught. That is the whole idea. Okay. Okay, guys. So let's say that I want to calculate the flux inside through a cubical surface. So how much that would be? Let's say I have placed a charge Q at the center of a cube. So what would be the flux through that cube, Aisha? Yeah. What would be the flux through that cube? I have placed.
Sir,
Yes, Mariam.
sir, are you screen sharing something?
No, I'm not screen sharing something because I'm not able to connect to my computer. So that is why I'm just talking and asking you some questions. So yeah, what would be, let's say that I have placed a charge inside a cube. So I want to calculate the flux through that cube. So what would be that? What would that be? Mayam, you tell. Yeah, so Aisha, you tell. Q by epsilon, right? And
Yeah.
then if I ask you, Mariam, that what would be the electric flux through one of the surfaces of that cube? So how much that would be? Yes.
Sir, how much?
Half. Yeah, so what I do is that, so how many surfaces are there for the cube? How many surfaces?
6.
6 surfaces, right? So for 6 surfaces, how much is the electric flux? Yeah, 6 surfaces are making it a closed surface, right? 6 surfaces are making it a closed surface. So for the 6 surfaces, what is the electric flux?
6 Q by epsilon
No,
0.
6 surfaces are making it a closed surface. So a closed surface has how much? A closed surface has how much flux? Yeah. Whenever I ask that if you have a closed surface, so how much the flux would be? Apply the Gauss law.
Yes.
6 by R.
Okay, so you have the flux inside a cube would be simply Q enclosed by epsilon naught, right? Right,
Yeah.
Maria? So a cube has 6 surfaces, right? And those 6 surfaces are making it a closed surface, right? So
Yes.
6 surfaces has the flux which is Q by epsilon naught. Am I right? Am I correct?
Yes.
So for 6 surfaces, the electric flux is Q by epsilon naught. So how much would be the electric flux for one surface?
1 by 6.
Yeah, flux by 6, which is Q by epsilon naught by 6. So that would be Q by 6 epsilon naught. Understood?
Yes, sir.
Okay, so let me quickly, so I wasted so much of your time, guys, because of this interruption, this network issues. So I will make up at some time later. Okay, so I will make up for that. Okay, guys. Yeah, so let me quickly open this Zoom and connect to the, let me quickly. Okay, so then I will am I audible, guys?
Yes, sir.
Okay, so today is a bad day, right? Yeah, so let me quickly connect my system and then we will discuss those problems. Yeah, so, okay. Yes. Yeah, so I am joining. Let me disconnect this and then I will join again.
Hello. Yes, guys, can you hear me?
Yes, sir.
Sorry, I am extremely sorry for today's class because yeah, I wanted to complete these topics and yeah, so okay. So let me share my screen and yeah. Okay, so let me share my screen quickly. What I will do is that yeah, I will take some extra day class and then I will complete those topics. Okay, guys.
Yes, sir.
So sorry about today. Sorry, I'm extremely sorry about today's.
It's okay, sir.
Yeah, Okay, so I am sharing the screen, but just okay. So give me 3 or 4 minutes more, guys. Right? Give me 3 or 4 minutes more. I will just quickly tell about this question, and then you guys can, yeah. So yes, who left? Okay, so Mariam has left. So what we will do is that okay, guys. Okay, so Mariam has come. Okay, so this is, yeah, this is still open. Okay, guys, so we will end the class here, right? Because so much interruption is going on, and yeah, so we will end the class here. Okay, we will discuss that later, and I will surely make up for that. Okay, guys, so whatever loss has been done today, I will surely make up for that. Okay, guys. Yeah,
Yes, sir.
yeah, please, please.